So now that power rule is about to get even better because we can combine it with other rules. So in particular, there are the derivative has certain properties. The properties of derivatives derive from the properties of limits, not necessarily in an obvious way. However, the first three that I'm going to show you are obvious, and then there's other ones that are trickier. So the first we're going to look at are like this. So I'm going to write it like this. A times the derivative of f of x. A f of x. I want the derivative of that. So the derivative of a f of x equals a f prime of x for any real number a. So a is any real number. All right? So why is that important? Because what if instead of f of x equals x squared, I had f of x equals 3x squared? Then f prime of x, or the derivative of x, equals 3 times the derivative of x squared. The derivative of x squared is 2x, so it equals 6x. So now you can sort of expand the idea of this rule a little bit more. Instead of just bringing the exponent up front, you're actually multiplying the exponent times the coefficient and then also dropping it 1. So this became x to the first power. So we're dropping that exponent 1. We're multiplying that exponent times the coefficient. All right? So for example, if I have f of x equals 10x to the 19th, then f prime of x equals, so I multiply the exponent times the coefficient. I didn't have to do that in my earlier examples because the coefficient was 1, but we're just saying if you do have a coefficient, you just multiply it. 190x to the 18th because we dropped that exponent 1. All right, multiply and drop it 1. So for example, if I have f of x equals 5x to the 7th, what do you think the derivative is? What do you think it is? It's 35x to the 6th, right? Multiply, drop it 1. All right, but it gets better because another important property is that if I have f of x plus g of x and I want to take the derivative of that, that's just the derivative of f plus the derivative of g. Now, you can actually combine this with this, use a equals -1, and you can easily derive that it also follows that f of x minus g of x prime is equal to f prime of x minus g prime of x. All right, so we can say in the kind of language you used for limits, because that's where these properties come from, the derivative of the sum is equal to the sum of the derivatives. The derivative of a difference is equal to the difference of the derivatives. All right, but you got to know this. The derivative of a product is not the product of the derivatives. Oh, do you ever wish that it was? But it's not. Likewise, the derivative of a quotient, also not the quotient of the derivatives. Now, we're actually going to prove why this is the case and prove what they really should be later. So what we're going to do for now is we're just going to say, okay, I can multiply a constant on my derivatives. I can add and subtract derivatives, but multiplication and division, those are out. That's going to have to wait until later this month. All right, so what can we do putting all those together? Well, we can do this. Suppose I had f of x equals 10x to the 5th plus 17x to the 4th plus 3x squared. Then I can just get f prime of x. So one way that we say this is we can do the derivative term-wise. Term-wise. So that means term by term, okay? Remember what we're going to do is multiply the exponents and drop them 1. We're going to multiply all those exponents and drop them 1. So we're going to have 50x to the 4th plus, what is that, 68? 68. 68. Why would I put a 17 there? X cubed plus 6x. So remembering that when I drop the 2 to 1, it just becomes 1. I don't have to write it. All these exponents are dropping 1. And then I'm multiplying. All right? Okay. Let's just remember that, suppose I have f of x equals 5x cubed minus 7x squared plus 13x minus 4. I mean, just pause for a minute and think if you had to plug in x plus h to all of those and then expand it out. It would be horrible. All right, so it's a good thing this thing works, huh? So f prime of x equals, so I'm going to multiply, drop it 1, multiply, keep the sign, multiply, drop it 1. Now, so what happens when you have a linear term is you have 1 and you multiply and you get the 13. But when I drop the exponent 1, I get x to the 0, which generally we're not going to write because it's just going to be 13 because x to the 0 is 1. Also, remember that the 4 is really 4x to the 0. So when I multiply, I don't get anything. All right. So without writing, the x to the 0 and the, this would be really, minus 0. X to the negative 1. All right, so we're not usually going to write that. We're going to just write f prime of x equals 15x squared minus 14x plus 13. All right? Now, look, there's something worth considering here. That so now you know that 5x cubed minus 7x squared plus 13x minus 4. When I do the derivative, I'm going to ignore the 4. That could easily have been 20. I just ignore it. Right? I'm going to have 15x squared minus 14x plus 13. All right? But if I had f of x equals just 5x cubed minus 7x squared plus 13x, and there was not a minus 4, my derivative would be the same thing. 15x squared minus 14x plus 13. It's the same derivative. All right? It's worth taking a moment to think about why. So let's think about this graph. I know quite a bit about it. I know it's a cubic, so it can have at most 2 turning points. I know that it can have at most 3 x-intercepts. I know that the end behavior is down up. Those are all things I learned in Algebra 2 and went over again in pre-calculus. So roughly speaking, I have some kind of a graph that looks like this, and that's this one. Okay? Now, what is the minus 4 doing that's different from this one? The minus 4 means I took this function, think of this as a parent function, and I did a vertical translation of 4 down. So this function will be exactly the same thing except 4 units higher, right? So that minus 4 means I went down 4 to get this graph, okay? So the blue graph is this one, and the red graph is this one, okay? Why are the derivatives the same? Because remember, the derivative gives the slope of the tangent at any point, the slope of the tangent. Well, if I look at any 2 corresponding points, the same x value, the slope is going to be the same. All the tangent lines are parallel because one graph is just a vertical translation of the other. So the slopes of the tangents are all the same for a particular x, for a given x. All right, so at any particular x value, the tangent lines are parallel. For a particular x value, the tangent lines are parallel. The slopes are going to be the same. That's why the derivatives are the same, even though this one has a minus 4 and this doesn't. So we have a very nice way to say this, a very important fact about derivatives that they like to find clever ways to test you about on the AP exam. I'm sure we'll see examples of it. The derivative, watch how nice, you guys who like literary ways of saying things are going to like this. It's poetical. The derivative is invariant under vertical translations. Right? Invariant, it doesn't change. The derivative does not change with a vertical translation. So if I have f of x and f of x plus a, where a is any real number, all right? These functions have the same derivative, And the reason is because they are essentially parallel curves. They are curves that are parallel at every point. Okay, but this power rule thing gets even better. You didn't think it could get better, but it can, and that's what we're going to see in the next video.